There is a spacecraft that NASA intentionally threw into Jupiter. On September 21, 2003, the Galileo spacecraft was guided into Jupiter's atmosphere where it was destroyed within seconds. This was not a failure. Galileo had cost $1.39 billion, operated for nearly 14 years, and returned some of the most important data we have about Jupiter. And when its mission was complete, NASA destroyed it on purpose because allowing Galileo to remain carried a risk NASA was unwilling to accept a risk created by Jupiter itself. And that same risk is why NASA does not attempt to go deeper into Jupiter. The data coming back from the probe didn't make sense. Scientists had sent the probe into Jupiter, expecting to find a wet, turbulent atmosphere rich with water vapor and active storms. Instead, the probe descended into one of the driest, calmest regions anyone could have predicted. The atmosphere was hot, much hotter than models suggested, and the winds were faster. The probe measured wind speeds exceeding 600 kilometers per hour, and those winds didn't decrease with depth the way scientists expected. They stayed strong even as the probe fell 150 kilometers below the cloud tops. But the biggest shock was the water, or rather the lack of it. Jupiter should be rich in water. The planet formed beyond the frost line, the region of the early solar system where temperatures were cold enough for water to freeze into ice. As Jupiter grew, it should have swept up enormous amounts of water ice along with everything else. The probe found water vapor, but not much, far less than expected. At the time, this was baffling. How could Jupiter be so dry? It took years to figure out what had happened. The probe had by pure chance descended into a hot spot. Hot spots are regions in Jupiter's atmosphere where the cloud deck has breaks allowing thermal radiation from deep inside the planet to escape. They're rare, covering only a small fraction of Jupiter's surface. They're also exceptionally dry because descending air in these regions suppresses cloud formation. The probe had essentially landed in Jupiter's version of a desert. It would be like sending a probe to Earth, having it land in the Sahara, and concluding that Earth is a dry planet. But even as scientists worked to understand the probe's data, Galileo itself was beginning its real mission, orbiting Jupiter and studying it from every angle. And what it found was stranger than anyone imagined. Jupiter doesn't just have an atmosphere. It has an atmosphere that extends thousands of kilometers deep with no clear boundary between gas and liquid. As you descend into Jupiter, the pressure increases. At the cloud tops, where the probe entered, the pressure is about 1 bar, roughly equal to Earth's atmospheric pressure at sea level. Go deeper and the pressure climbs rapidly. At about 1,000 kilometers down, the pressure reaches about 200,000 bars. That's 200,000 times the atmospheric pressure on Earth. At this depth, hydrogen stops behaving like a gas and starts behaving like a liquid. But it's not ordinary liquid hydrogen. Under these extreme pressures and temperatures, hydrogen enters a state that doesn't exist naturally anywhere, music, on Earth. The electrons are stripped away from the hydrogen atoms and the hydrogen becomes electrically conductive. It behaves like a metal. This is called liquid metallic hydrogen and it makes up most of Jupiter's interior. Somewhere between 75 and 90% of the planet's mass exists in this state. The temperature at this depth is estimated to be around 10,000 degrees Celsius. The pressure is millions of times greater than anything we can create in a laboratory. And the metallic hydrogen is churning, convecting, music, driven by heat escaping from Jupiter's core. This convection combined with Jupiter's rapid rotation generates Jupiter's magnetic field. And that magnetic field is extraordinary. Jupiter's magnetic field is the strongest of any planet in the solar system. It's about 20,000 times stronger than Earth's. At Jupiter's equator, the magnetic field strength is roughly 4.3 G. At the poles, it reaches 14 G. For comparison, Earth's magnetic field at the surface is about 0.5 Gauss. This powerful field extends far into space, creating a magnetosphere that dwarfs anything in the solar system except the Sun's. Jupiter's magnetosphere stretches 7 million kilometers toward the Sun and extends more than 600 million kilometers in the opposite direction, reaching all the way to Saturn's orbit. Inside this magnetosphere, charged particles are accelerated to nearly the speed of light. The radiation is intense enough to destroy spacecraft electronics in hours. Galileo was designed with heavy radiation shielding. But even so, the mission planners knew the spacecraft had a limited lifespan in Jupiter's radiation environment. And deep below all of this, hidden beneath thousands of km of hydrogen, lies Jupiter's core. Or at least that's what scientists thought. For decades, planetary scientists assumed Jupiter had a dense, compact core at its center. Models suggested this core was made of rock and ice with a mass somewhere between 10 and 20 times Earth's mass. This made sense. In the core accretion model of planet formation, Jupiter would have started as a rocky seed that grew large enough to gravitationally capture gas from the surrounding solar nebula. The core came first, the gas came later, but then Juno arrived. NASA's Juno spacecraft entered orbit around Jupiter on July 4, 2016. Its mission was to study Jupiter's interior by making precise measurements of the planet's gravitational field. Gravity isn't uniform. If a planet has a dense core, its gravitational pull will be slightly stronger over that core. By measuring tiny variations in gravity as Juno, MUSIC, orbited Jupiter, scientists could map the distribution of mass inside the planet. The data Juno returned was shocking. Jupiter's core isn't compact. It's not a solid ball sitting at the center of the planet. Instead, it's diffuse, spread out, occupying up to half of Jupiter's radius. The core appears to be a mixture of heavy elements gradually blending, MUSIC, into the metallic hydrogen above it. There's no sharp boundary, no clear division, just a gradual transition from dense material to lighter material over thousands of kilometers. This was not what anyone predicted. Scientists scrambled to, MUSIC, explain it. One theory suggested that Jupiter was hit by a massive object early in its history, something 10 or more times Earth's mass, colliding with Jupiter and mixing its core with the surrounding gas envelope. Computer simulation supported this idea. A head-on collision with a large planetary body could have shattered Jupiter's core and created the fuzzy dilute, MUSIC, structure Juno observed. But other simulations contradicted this. When researchers modeled giant impacts in detail, they found that even a violent collision wouldn't permanently mix the core material with the gas. Over time, the heavy elements would settle back down, reforming a compact core. The fuzzy core should be temporary, but Jupiter's core has been fuzzy for billions of years. A newer theory suggests the fuzzy core formed gradually during Jupiter's growth as the planet accreted material in a chaotic, uneven process. This would explain why Saturn also appears to have a fuzzy core. Two fuzzy cores in two giant planets suggests a common formation process, not a random collision. But the truth is, we don't know. We don't know how Jupiter's core formed. We don't know if, MUSIC, it's stable or slowly dissolving. We don't know how it connects to the metallic hydrogen above it or how it influences Jupiter's magnetic field. What we do know is that going deeper into Jupiter gets harder and more dangerous the farther you go. Jupiter kills spacecraft. This isn't an exaggeration. The radiation environment around Jupiter is lethal to electronics. Charged particles trapped in Jupiter's, MUSIC, magnetosphere bombard anything that gets close, causing cumulative damage that eventually leads to failure. Galileo was built to survive this. The spacecraft carried heavy shielding around its most sensitive components. Its computer systems used radiation-hardened processes. Every circuit board, every wire, every sensor was designed with Jupiter's radiation in mind. Even so, Galileo barely lasted. Over the course of its mission, Galileo completed 34 orbits around Jupiter. Each orbit took it through different parts of the magnetosphere, exposing it to varying levels of radiation. The cumulative dose was staggering. By the end of the mission, Galileo had absorbed radiation equivalent to 60 million dental X-rays. That's enough to kill a human thousands of times over. The spacecraft's cameras failed. Several instruments stopped working. The onboard computer experienced memory errors. Juno faces the same challenge. The spacecraft's orbit was carefully designed to minimize radiation exposure. But even so, Juno is slowly dying. Two of its instruments, the infrared auroral mapper and the camera, were expected to fail by the 8th orbit. Music, the microwave radiometer, was designed to last through orbit 11. As of now, Juno has completed, music, 37 orbits and is still operational, but the clock is ticking. The deeper you go into Jupiter, the worse it gets. The strongest radiation is concentrated in a belt that loops around Jupiter's equator between the planet and its innermost moons. This is where charged particles from Io's volcanoes are ionized and accelerated to near light speeds. Any probe attempting to descend deeper into Jupiter would have to pass through this belt. The radiation would be intense enough to fry electronics in minutes. But radiation isn't the only problem. The Galileo atmospheric probe survived for 57 minutes before it was destroyed. The cause of its failure wasn't the heat. It wasn't the winds. It was the pressure. When the probe signal stopped, it was 150 kilometers below the cloud tops at a pressure of about 23 atmospheres. That's 23 times the pressure at Earth's surface, enough to crush the probe's transmitter. And the probe was still in the upper atmosphere. It hadn't even reached the region where hydrogen transitions from gas to liquid. If you wanted to send a probe deeper to study the liquid hydrogen ocean or the metallic hydrogen layer or the core, you would need a vessel capable of withstanding pressures millions of times greater than what the Galileo probe experienced. No such vessel exists. The deepest anyone has ever sent a probe on Earth is about 11 kilometers to the bottom of the Mariana Trench. The pressure there is about 1,100 atmospheres. The vessels that go there are small, spherical, made of titanium, and they can't carry much in the way of instruments. To reach the depths of Jupiter, you would need something far more robust. A probe capable of surviving pressures exceeding 1 million atmospheres. Temperatures of tens of thousands of degrees. Radiation that would destroy any known material in seconds. And even if you could build such a probe, how would it transmit data? Radio waves don't penetrate liquid metallic hydrogen. Any signal from deep inside Jupiter would be blocked by thousands of km of electrically conductive material. You would need a relay system, multiple probes at different depths, each passing data upward to the next until finally a signal could escape to a waiting orbiter. The engineering challenges are immense. The costs would be astronomical. And for what? To answer questions about Jupiter's interior that may not even be answerable with our current technology.